Hello everyone, my name is Yizhou Shan. Today I'm presenting our work, Disaggregated Persistent Memory and Controlling them Remotely, Exploration of Passive Disaggregated Key-Value Stores. This is a joint work with Shin-Yeh, Tsai, and Yiying, Zhang from Purdue and UC San Diego. A recent trend called resource disaggregation breaks monolithic servers into network-attached resource pools. It offers better manageability, enables independent scaling, and tight resource packing, and therefore has attracted more attention and adoption in academia and the industry. Notably, disaggregated storage, which separates compute and storage pools, has been a common practice in current data centers and clouds like AWS, Facebook, and Snowflake. Alibaba lists faster disaggregated storage as a major enabling factor of their huge single-state sale need. Disaggregated storage enables flexible management and independent scaling of these data center storage systems. More recently, with networks getting faster and applications hitting a memory capacity wall, data centers like Microsoft, Huawei are turning into adding more memory as remote or disaggregated memory. With more memory, we can run more types of big data applications. So how about persistent memory, or PM? Like DRAM, PM is byte addressable and has similar performance. Like SSD and disk, it is durable and power resilient. If we can disaggregate PM, it can enjoy disaggregation's management, scalability, and utilization benefits. It will also be an easy way to integrate PM into current data centers. Can we use existing disaggregate systems for DPM? The answer is no, because current disaggregate storage systems are designed for SSDs and hard disks. Their software system will be too slow for PM. On the other hand, disaggregated memory systems do not provide data durability and reliability mechanisms and cannot be used either. So how shall we build disaggregated PM? To answer this question, let's first review the spectrum of today's PM deployment models. On the far left side is the non-disaggregation mode, or traditional distributed PM mode. Regular servers are connected by the data center network. Each server runs application computation and hosts some PM. Some of the PM is used locally, some is used by remote servers. In addition, each server runs a PM management layer. There are several notable systems in this area already. At the center is what we call the active disaggregation mode. Regular servers on the left side run application computation. PM nodes on the right side host PM and run the management layer of this PM. There have been quite a lot of systems that adopt the active disaggregation model, although most of them are DRAM or SSD based. Both non-disaggregation and active disaggregation have been extensively studied and adopted in the real world. However, there's a completely unexplored area, an area we call passive disaggregation. Like active disaggregation, regular servers run applications and PM nodes host PM. But instead of running the management layer within the PM nodes, passive disaggregation runs at the computer servers. This work, for the first time, does a thorough study of passive disaggregation model. With our pDPM model, PM devices only need to have NIC and PM, and they're accessible only via network. In addition to its disaggregation benefits, pDPM has low CapEx and OpEx, and avoids any scalability bottlenecks at PM nodes. Moreover, pDPM is an unexplored research area. Studying it would answer many questions and serve as a guide for future PM research. One thing worth mentioning is that pDPM is possible now, thanks to today's faster data center network and technologies like RDMA that can bypass CPU. With this new hardware model, the natural and most important question is, without processing power at the PM, where and how shall we process and manage data? A most straightforward way is to run everything, including data accesses and PM management at compute nodes, or CN. This architecture essentially distributes both data and control planes to all CNs. A different way is to centralize data and control planes. For example, by adding a centralized coordinator between CNs and DNs. The coordinator could perform all metadata operations and coordinate data accesses from CNs. A third way is a hybrid model that combines distributed and centralized approaches. For example, the data plane can be performed as CNs in a distributed way, and control plane could be carried out at a centralized server. Based on these three architectures, we designed and implemented three key-value stores: pDPM direct for the first model, pDPM central for the second model, and Clover for the hybrid model. We performed extensive experiments to evaluate the performance, scalability, and the cost of these three systems. Overall, we find that Clover, which is our final pDPM product, is the best model among the three, and it achieves similar performance as the active pDPM model, but at a lower cost. We also discovered interesting trade-offs between active and passive DPMs. For the rest of today's talk, I will go through these three systems one by one and present their evaluation results. All these systems guarantee that reads only see committed data and writes are always atomic and are able to recover from power failures. Now let's take a closer look at the pDPM direct. In this mode, CNs are regular servers that access and manage DNs directly via one-sided RDMA. Both data and control planes run within CNs. The key feature of pDPM direct is the distributed, unorchestrated CNs, which results in two design challenges: how to efficiently coordinate the management of DN space, and how to coordinate concurrent reads and writes across CNs. Our solution to space management is to pre-assign two spaces for each key entry, one committed space for reads and one uncommitted space for in-flight writes. By pre-assigning static spaces that are accessible by all CNs, we avoid the need to coordinate space allocation and deallocation at runtime. In addition, we introduce a lock-free read to ensure reader integrity with help of a per-entry checksum. Finally, we introduce an efficient RDMA-based write lock for concurrent writers. These read and write mechanisms require no coordination across CNs, which enable good performance with the pDPM direct model while delivering our synchronization guarantees. To perform writes, CN first uses RDMA compare and swap to acquire the remote lock. Once acquired, CN will use RDMA write to write the data and checksum into the uncommitted space, serving as a redo copy if a crash happens in the middle. After that, CN uses another RDMA write to write the data and checksum into the committed space. At last, CN uses a final RDMA write to unlock the remote entry. To read an entry, CN issues an RDMA read to read the committed data and the checksum. CN then calculates the checksum of the data just read and compares it to the checksum read from the DN. If they match, then the read operation finishes. Otherwise, it means the data is being modified by a concurrent writer. The CN will then repeat the process until checksums match. In the best scenario, a key writes latency is 4 RTTs with 1 checksum calculation time. A key reads latency is 1 RTT and 1 checksum calculation time. There are several drawbacks of pDPM direct. Writes are too slow. Reading and writing large data entries are slow because of checksum calculation time. And because of write lock, it has poor scalability under heavy contention. pDPM direct's shortcomings are due to its distributed data and control plane nature. In pDPM Central, we add a global coordinator to manage and serialize accesses. Let's see if this could help. The central coordinator is a full-fledged server that manages DN space and serializes data accesses. CNs communicate with the coordinator with two-sided RDMA. The coordinator communicates with DNs with one-sided RDMA. With such a centralized coordinator, it's much easier to manage DN spaces and coordinate concurrent accesses. To leverage the centralized architecture, we design pDPM Central by putting all metadata and control logic at that coordinator to avoid distributed coordination. For example, the coordinator is the only party that allocates and deallocates all DN spaces. It maintains a key entry location mapping table locally, which contains all the metadata information. Each entry in this table has a pointer pointing to the physical location of the entry. We also use a lock, local per entry lock, only for synchronization across multiple threads running at a coordinator. To write a key entry, a CN sends an RPC request along with new data to the coordinator. After receiving a write request, the coordinator allocates a new space for it. We perform out-of-place write for crash recovery. The coordinator then writes the new data to this new space. Then, the coordinator logs the corresponding entry in its local mapping table and updates the pointer to the new location and releases the log. Finally, the coordinator replies CN's write RPC request. To perform a read, CN sends an RPC request to the coordinator. The coordinator then logs the corresponding entry in the mapping table, then reads the data from the location stored in the table, and finally replies CN's read RPC with this data. Reads and writes in pDPM Central always take 2 RTTs. However, pDPM Central's 2 RTT KVS read is slower than pDPM Direct. More important, the single coordinator cannot scale with CNs or DNs. Now I have walked through the direct and the central modes. Both have pros and cons. For direct, 4 RTT write is slow, and checksum calculation for large data is also slow. For central, reads incur an extra RTT, and the coordinator cannot scale. At high level, direct uses distributed data and control planes. Central uses centralized data and control planes. To mitigate the drawbacks of these designs, we propose to separate data and control planes. Now, I will present our final pDPM product, Clover. Our main idea is to use a distributed data plane and a centralized metadata plane. To cleanly separate these two planes, we use different locations, different communication methods, and different management strategies for them. For the data plane, CNs directly access DNs use one-sided RDMA. For the control plane, CNs talk to one or few global metadata servers, or MS, with two-sided RDMA. We will first look at the data plane and then the metadata plane. The main design challenge of Clover's data plane is similar to pDPM Direct: how to efficiently support concurrent data accesses from CNs to DNs. But the key difference from Direct is that Clover could rely on its efficient metadata plane to perform data operations in a way that's not possible with Direct. Remember that Direct uses write log and checksum for each entry, which causes 4 RTT writes. This is because that synchronization is unavoidable to the fixed location of each entry. Instead, in Clover, space allocation is more efficient. Therefore, we design a log-free, out-of-place write mechanism. We also introduce several optimizations to further reduce read and write RTTs. Now let's look at some details, starting from the log-free data structures. Each data entry at the DN is a chain of multi-version redo copies. Each key entry is a chain. Each version within the chain has a header and actual data. The header has some metadata and a pointer pointing to the next version in the chain. If the pointer is empty, it means this version is the tail and the latest. To quickly find the latest version of a key entry, each CN has a simple data structure called a cursor that points to a version that this CN thinks is the latest version. But this cursor may be outdated. We will see that in a bit. At a high level, Clover's key write is out of place. It creates a new redo copy version, which will be linked onto the chain. Let's say CN1 now wants to write a new data D1. It first uses RDMA write to write the new data to a new location in the DM. Since CN1's local cursor points to D0, it will perform a RDMA compare swap to atomically chain D1 onto D0. Locally, CN1 will also update its cursor to reflect this change. Now assume CN2 also wants to perform a key write. Similarly, it will do an out-of-place write to D2. But the cursor at CN2 still points to D0, so CN2 still thinks D0 is the latest. So CN2 will try to link D2 onto D0. But this would fail since D0 is not the latest anymore. After this failure, CN2 will know that the latest is now is D1. So it will try another compare and swap to link D2 onto D1. Similarly, CN1 writes another D3. In Clover, KV read always returns the latest version. In this particular case, version D3. Recall that cursor points to the version that this particular CN thinks is the latest. So if CN1 wants to do KV read, it will first try to read the version D1. After receiving the data, CN1 will check if this is the latest by checking whether the pointer is empty. If not, it will do chain work until it finds the latest version, D3. In total, it takes CN1 3 RTTs to reach the latest version. The reason CN1 needs to do chain work is that there are concurrent writers CN2, which will make CN1's cursor outdated. Chain work might be very long when there are many heavy concurrent writers. To mitigate this issue, we introduced an optimization called shortcut read, a technique inspired by skip list. We add a shortcut pointer in DN for each KV entry, and this shortcut mostly points to the latest version, but not guaranteed. Shortcut location is fixed so CNs know where to find them. Shortcut read works as follows. The CN will first read the shortcut pointer from DN and learn that D3 is the latest. The CN issues another RDMA read to read D3. It's able to finish within 2 RTTs. So now, when CN wants to do KV reads, it not only issues the normal chain work read procedure, but also performs a shortcut read at the same time. The KV read returns when the faster one finishes. In Clover, when the contention is low, KV write is only 2 RTTs and KV read is 1 RTT. Now let's look at Clover's metadata plane. The main design question here is how to provide low overhead, scalable metadata service. Different from Central, Clover's centralized metadata plane is not in the middle of the data plane, which brings both new opportunities and challenges. We'll leverage the opportunity that metadata server is not in the middle of data access to further move all metadata operations off performance critical paths. The challenge though is now we need to distribute metadata decisions to CNs. We solve this challenge by batching operations and avoid cache invalidations. The end result is that we have a clear separation between data and the metadata planes. Now let's look at some details. Metadata server, or MS, in Clover performs space allocation, garbage collection, and global load balancing. Recall that Clover needs a new space for every write. This requires very intensive space allocation. So instead of asking MS for a new space at every write, CNs acquires a bunch of new spaces at a time from MS. MS keeps a list of spaces and assigns them in a batch to CNs. Clover creates a new data version for every write. All the older versions need to be recycled. To move this recycling operation off the performance critical path, we let CN send the retire requests asynchronously and in a batched way to MS, which in turn feeds them into free list for future allocations. Clover also ensures data durability for both data and the metadata planes. To provide data durability, Clover built a chaining replication mechanism in which Clover links the version to all the replicas of the next version. It works as follows. Please check out the paper for details. Clover leverages these distributed copies to balance loads. Both MS and CN are able to carry out load balancing policies. In addition, Clover ensures metadata plane reliability by using shadow MS servers. Coming back, now we have covered all 3 types. For Clover, Thanks to its separate data and metadata plane design, it can offer good read and write performance, and can also scale with large number of CNs and DNs. In order to understand the pDPM systems and how it compares to active DPM, we carry out an extensive set of experiments. We run 3 pDPM systems: pDPM Direct, pDPM Central, and Clover. We run 2 non-disaggregated systems, Octopus and Hotpot, and the two-sided QVS called HERD. We also port HERD to Bluefield SmartNIC. Both of them serve as active DPM systems. We use a cluster of 14 machines, each one with 100 Gbps RDMA NIC, connected via a 100 Gbps IP switch. We were not able to get hold of entire persistent memory, therefore use a DRAM to emulate persistent memory performance. We first measure the latency of KV read and writes. 1 CN synchronizes the read-write KV entry. Our latency baseline is RDMA verbs read and write. Clover's read is very close to raw verbs read. Clover's write is worse than read because write has an extra RTT and some protocol processing time. As expected, pDPM direct latency increases dramatically when request size increases, at which point the checksum calculation time dominates. Central's read-write latency is always around 2 RTTs. For writes, HERD outperforms Clover and other pDPM systems because two-sided communication allows it to complete the writes within 1 RTT. HERD Bluefield is worse than others due to low profile on-calls. Overall, Clover has the best read-write latency among 3 pDPM systems. Its read is close to raw DMA, write is around 2 times of raw DMA. We also run YCSB. We run 3 pDPM systems and Octopus, a non-disaggregated system. There are 4 CNs and 4 DNs. Each CN performs 1 million requests on 100K KV entries following a zip distribution. All numbers are aggregated. The first 3 bars are direct, central, and Clover. Overall, Clover is the best performing pDPM system. The left table shows the median, average, and the 99th percentile RTTs of Clover. Clover requires only 1 RTT for read most workloads. And even for 50% writes, Clover only incurs 6 RTTs at the 99th percentile tail, and 1 RTT at the median. Octopus has much worse performance. Another non-disaggregated system, Hotpot, has similar performance. Overall, Clover outperforms non-disaggregated PM systems. We also conduct experiments and analytics to demonstrate that Clover's CAPEX and OPEX are both lower than active disaggregation and non-disaggregation. In today's talk, I reviewed the spectrum of the data center PM deployment model and took a deep dive into an unexplored research area called passive disaggregated PM. Our results show that the pDPM offers deployment and cost benefits, and it's totally possible to get optimal performance with the pDPM model. But achieving it is hard, and it may not always be possible, as what we see with heavy write contention case. The key to a good pDPM design is a clean separation of data and metadata planes, and Clover demonstrates the various challenges and benefits in doing so. We believe our findings of pDPM can also be applied to disaggregated DRAM systems and many future systems. Before I end my talk, I want to share some of my final thoughts after this multi-year-long project. First, as we discover the trade-offs in both active and passive disaggregation, we believe that the best way going forward is a hybrid model. For example, by offloading some computation to low-cost, programmable disaggregated hardware devices. As for research efforts, this work is unique in that it does not go with where the crowd goes. Doing so, of course, is risky, but after all, we find it to be a rewarding experience, since we discovered many new possibilities and limitations, and we also got inspiration from it along the way. All our systems are open source. If you have any questions, please reach out to us. Thank you for listening.